Hello, everyone. Uh, hello, everyone.
Hey.
You hear me?
Yep.
Just give me a moment because I just finished the reading. So I have to set up something. Sorry about that. You can just try to take a glance of your exams, and we will go through it very soon. Okay? Bless you. And again, well, for those who just arrived, you can take a glance of the exam, and we will go through it very soon. I just finished the reading. Sorry, I didn't finish the earlier. You can just watch it and see, well, whether there are some mistake or not that I made.
Professor, is it on Sakai?
Yeah, it's on Sakai, so you can check it. Let me see. I'm sorry, because I just changed something of my camera, so I have to set it up. And I think it will be done. Okay, great. Oof. Okay, I finally got it.
What's wrong?
There's echo.
I know. Okay. Okay. I think it works now. It should work now. Oh, sorry for being late. The setup of my of my working room is a bit mess, but now I think it works. So I believe you all see your exams at this moment. So today, before we go through some new materials, which is chapter 5 of the STANS book, what we are going to do is, well, we will go through our midterm first, okay? We will go through it and try to check, well, for what part of this PDE things we've learned during the last 3 weeks, why does it not quite work for you? Okay. Well, to be honest, I didn't realize that this exam is as hard as this. So I'm kind of surprised about it because well, before yesterday, I was just thinking that whether I make this exam over too easy or not. Well, unfortunately, it's not. Well, unfortunately, it's over too hard. There might be some reason. Maybe next time I will try to give you more hint on it. Maybe I didn't really show you why this part or this kind of knowledge we've learned are so important and which part is so important. Okay, so maybe I should emphasize a little bit more on this kind of thing and tell you more about this, maybe somehow big picture so that you will know which part would be the most significant part of this course, okay? And before we move on, and also I think I should announce that since this time nobody are doing really well in this exam, so I try to normalize this exam, which I don't really want to do that, but I have to do that. And the way I try to normalize it is I try to take the geometric average of your real scores and 100, okay? So that is the score that will be count as your midterm score, okay? And you can see that from your Sakai. And you can also see, your exams after my grading on Sakai, okay? And I hope you have already seen that or download it and are able to open it. If you're not, I recommend you to do that because then it will be easier for you to understand what I'm saying, okay? And you will get some idea about what's the difference between your idea and the solutions idea of the exam, okay? So let's try to do it one by one, okay? By the way, so before we move on, any questions other than this, exam stuff? Any other question? I'll go through it, don't worry. And other than the problems, do you have any question? No? Okay. So let's try to go through it and see, why I think it's over too easy, but it seems over too hard for you, okay? Maybe we can find the reason eventually. So for the first one is just to ask you to copy it down and try to sign for the honor code. So For the second problem, that okay? For the second problem, it asks you, okay, I gave you fx, which equals to 1 plus 3 cosine x, cosine 3x, I think. Let me see. Let me make sure I got the correct, right, in the same stage. Yeah, cosine 3x. But this doesn't matter, actually. You have fx equals to 1 plus cosine 3x. And we call fk to be f convolved with f, convolved with f, and so on, convolved with f, with totally k times. Okay? And then the question is, I ask you to find the limit as k goes to infinity, fk evaluate at pi. For this problem. Well, for this problem, the thing is, I try to test you, well, the understanding of this convolution operation of functions. Of course, the definition of convolution is sort of complicated because it's involving the multiplication of these two functions and then take the integral. Okay, so if you have this kind of functions which looks very, well, not very pleasant when you try to do the integration, then probably to compute the convolution is something painful. Okay. However, if you still remember when we introduced the convolution operation, I think I said that if you don't remember, then I will say it again. The reason why convolution is so important when we try to study the Fourier analysis or Fourier series is simply because if you have the convolution of two functions, and if you try to find the Fourier coefficient of this convolution function, what you will get is the multiplication of this Fourier coefficient of these two functions separately. Okay, so in some sense, the convolution of a function of two functions just means you try to do multiplication on the Fourier coefficient of them. Okay, so this is why the convolution operation is so important, because it just in the same place as multiplication. Okay, it just plays the same role as multiplication. Which is why sometimes when you try to use some software like MATLAB to do some numerical solution, to find the numerical solution of some PDE, and you try to use something like the Fourier transform, or try to use a Fourier coefficient or Fourier series to find that, to find the solution, then this convolution would be very important. Okay, in MATLAB it has a comment, say CONV means the convolution of two functions. However, the calculation of CONV is very slow. This function is sort of slow. So which means when you try to do the numerical coding of this kind of problems, for instance, you have two functions and you try to compute the convolution of these two functions for some reason, which we will probably see in next week, why we need to compute the convolution of these two functions, then you don't really want to do the convolution. What you really want to do is you try to write f in terms of the Fourier coefficient or in terms of the Fourier series, and you try to write g in terms of Fourier series. Okay, and then the convolution is just a new function with the new Fourier coefficient. Right? Then this makes the problem much, much easier. Maybe you think that, okay, since the convolution is over too hard, then can we say that, okay, to expand this function as a Fourier series, is that a very complicated computation for MATLAB or for some other software? If you have this question, then that would be a very great question, because this is something that discussed on chapter 7 of this of Stan's book, which basically says that, well, if you have a function and you want to find, this function is periodic, and you want to find the Fourier coefficient of this function, okay? You want to find the Fourier coefficient of this function. It seems that you have to compute all this kind of integral of this function. It seems very hard. It seems very hard for MATLAB. It seems very hard for all the softwares. However, well, there is a very, very great algorithm invented, I think, in last century, which is so-called the fast Fourier transform, FFT, or DFT, okay? This FFT, fast Fourier transform, is a super fast algorithm in order to compute the Fourier coefficient of a function. So whenever you give me the function, I can compute the Fourier coefficient for you with very, very fast algorithm. Okay, so in MATLAB, the common should be FFT of a function. And this comment or this function is much faster than the convolution. Okay, so which is why when you have this kind of functions, and you have, well, this kind of functions, and you try to do this kind of operation like convolution, then you should try to think somehow what happens on the Fourier side, what happens on the Fourier coefficient. So for this problem, okay, you have a function, and he asks you to find the convolution of this function k times, and what happens to this function. Then what we do know is fk is a convolution by f k times. So the Fourier coefficient of fk, although the convolution, the expression of fk is very hard, it's very complicated, but the Fourier coefficient of fk is super simple, right? It's just f, the Fourier coefficient of f at n to the power k. Okay, nothing more than this. So that means, okay, as long as we know the Fourier expansion of fx, we are able to compute the Fourier coefficient of fk. So what would be the Fourier expansion of this fx? How can you find the Fourier expansion of fx?
Well, usual formulas where like we look for Fourier coefficients using integrals and stuff.
You could do that. That's definitely true. But if you remember, well, this is something this is something maybe I know. Well, when I set up this this midterm, because this is something, well, which is slightly different from what I thought, because I think since you have done the homework problems, you remember we have the homework problem saying that, okay, if you have the Fourier, well, if you have the Fourier expansion f written as an e to the in theta, we can also write it as the summation of cosine function and sine function, right? So it's a0 plus, well, something like capital AN cosine and theta plus, well, n is greater or equal than 1 n is greater or equal than 1, bn sine n theta. Okay, so which means it's very easy by the Euler's formula to transform all of our complex form of the Fourier expansion to this real form of the Fourier expansion, right? It's just something like we explained it by saying that e to the I n theta is just a cosine n theta plus I sine n theta. So which means it's very easy to write this kind of expansion in terms of cosine and sine. This is not very hard, right? But if you understand it, that also means another thing, which is in the real life or in practice, we don't really have those kind of functions that really looks like this e to the I n theta, right? But in practice, if you have a periodic function, more or less, it should be some functions like sine function or cosine function, right? Then the question is, how can you transfer this cosine function and sine function, for instance, this kind of function, to something like this, something like e to the I n theta? If you are able to do that, then you automatically get the Fourier expansion of this function. So which means for this function, fx is actually equals to 1. You can definitely transfer this cosine 3x into e to the I n theta or e to the I n x. Because you are able to translate this kind of language to cosine sine. Of course, you can also go back from cosine sine to this kind of functions, right? So which means we can write, as Langchen said, we can write fx to be 1 plus cosine 3x. It's 1/2 e to the I 3 theta or 3x, right? Well, plus e to the minus I 3x. Right? This gives you cosine 3x. But meanwhile, you can see that this is also a valid Fourier expansion, right? So which means the Fourier coefficient of f must agree with this form. So which means f hat of n should equals to 0 if n is not equals to plus or minus 3 or 0, right? And f hat of 0 should equals to 1. F hat of 3 should equals to 1/2. F hat of minus 3 is equals to 1/2. Okay? So in practice, if you have some sine cosine function, it actually tells you what is your Fourier series looks like. Is that clear?
Yep.
Okay. So this means for fk, we must have the Fourier expansion similar to this f, right? So it's still like 1/2, but with power k here. This is f, the Fourier coefficient of f when n equals to 3. And then for fk, the Fourier coefficient should be 1/2 to the power k. E to the minus I 3x plus, okay, 1 is still 1, and plus 1/2 to the power k e to the I 3x. Okay, So we know that the limit as k goes to infinity, fk of pi gives you 0, 0, 1. Okay, so this is how you solve the first problem. Is this clear?
Yep.
Okay, unfortunately, nobody really do it like this. So, but some of you compute several of this convolution and find, well, the pattern, and then, well, you can show this. But I think for the first problem, it's supposed to be easy, but it seems that nobody really have this kind of idea, and we don't really do this kind of practice a lot. So probably that's the reason why it seems pretty hard. Okay. Any question? Okay. Then for the second problem, he says that if you do have a function which is well, f prime is integrable or is continuous, then we must have, well, and f is also continuous because it's differentiable, so it's continuous. Then we must have the Fourier series of this function converge to f uniformly, because we have the Fourier coefficient of this function converge absolutely. Okay, and the f is continuous, so we have this Fourier series must converge uniformly. And he wants you to show it in this way by using an inequality, which is the summation of the absolute value of fn, f hat n, can be bounded about by f hat 0 plus the summation of 1 over n squared with half power here times, well, the integral 1 over 2 pi from minus pi to pi f prime of x square dx. There's a typo here, I'm sorry. You want to prove this kind of thing. Okay. And for this problem, I think most of you did it quite well, correctly. Yeah, I think most of you did it very well, because you can imagine, as we said, the f hat n and f prime hat n, they also have the relation, which is the key reason why we are interested in this kind of Fourier coefficient. It's simply because when you take derivative, then the Fourier coefficient will just change like multiplication by some number, right? So which means f hat of n is equals to, f prime hat of n is actually equals to in times f hat of n. Okay, so that means f hat of n is equals to 1 over in f prime hat of n, right? Okay, that's good. And if you take f's value, then you take f's value here as well. Then if you take the summation, well, to prove it rigorously, I think we'd better not to write the summation to be infinite many terms, because we don't know whether it's converge or not. If it doesn't converge, then we cannot do any inequality for this sequence, okay? So let's say n is less or equal than n, and see what happens for this partial sum. F hat of n with f's value is equals to n is less or equal than capital N, okay? 1 over n f prime hat of n. you can see that you write this kind of summation to be some summation with two parts. Okay? Then what we can do is we can try to treat this kind of summation like an inner product of 1 over 1, 1 over 2, and so on, 1 over n until 1 over n, multiply with inner product with f prime hat 1, f prime hat 2, f prime hat until f prime hat n. And then what we can do is so-called the Cauchy-Schwarz inequality. Okay, we can use the Cauchy-Schwarz inequality, say that, okay, it's less or equal than the norm of this sequence, which is 1 over n squared with power a half. This is a norm, or the L2 norm, little L2 norm of this sequence, although it's finite, but we can still say it's the little L2 norm, okay? Times the little L2 norm of this sequence, f prime of n, well, f prime hat of n squared with power a half. Okay? And we know that, well, plus f0, of course, because f0, you cannot write it this way. And we do know that well, the summation of 1 over n squared, it converges, right? So it's less or equal than the summation of all the n, 1 over n squared with a half. This is a constant. This is equal, well, I think you did your homework. This constant equals to pi square over 4 or 4 over pi square. I forgot that number, right? This is the number. Times for any n, f prime hat of n squared with power a half, right? So this is less or equal than f hat 0 plus, this is just a number, some pi. And this one, you can use the Passoir identity, right? Well, this is little L2 norm of the Fourier coefficient of f prime. Of course, it equals to the integral norm of f prime. F prime square dx from minus pi to pi 1 over 2 pi with power a half. Okay, this is true for any capital N. So that means we can take n goes to infinity, we still get this inequality. So which is why this part, well, this summation is bounded above, and you have this inequality. Okay, so this is just a Cauchy-Schwarz inequality here. And if you are not familiar with this Cauchy-Schwarz inequality, that is also possible. But I just hope that you are familiar with this kind of inequality, because it is very important in analysis. Okay, it might be the most important inequality in analysis, which is you have the inner product of two functions or two vectors, then that value is less or equal than the norm of this function times the norm of the other function or the sequence. Okay, so this kind of inequality is the most important inequality in analysis. although we haven't used a lot for this inequality, but I still hope that you could understand, well, when shall we use this inequality? Okay, any question?
Professor, can you explain a little more about like when we use this inequality, how did the second like sigma comes from? The second sigma.
This one. Second sigma. Which second sigma?
Yes, this one.
This one.
Because like previously we just have like one sigma, but like why it becomes two?
Well, you can see what's this? This is like 1 over n has a sequence, right? It's a sequence on little L2 with inner product with this f prime hat of n as a sequence in little L2 space, okay? This is the inner product of these two sequence. This one, it's the inner product of these two sequence in little L2 space, right?
Mm-hmm.
Then it's less or equal than the little L2 norm of this sequence times the little L2 norm of this sequence, right?
Yes.
And if you write it, the little L2 norm of this sequence is the summation of 1 over n squared with half power, right? And the little L2 norm of this sequence, again, this is a sequence, is you take f prime hat of n squared with half power, okay?
Okay.
This is why you have the summation here as well, because it's just the little L2 norm.
Mm-hmm. I see. Thank you.
Mm-hmm. Any other question? Any other question? Okay, then let's see 3. Actually, the first 3 problems, when I set up these 3 problems, I just saw that because the problem number 3 is just some corollary of problem number 1, 2, or it's just you can use the idea of problem 1 and problem 2 to get problem 3 easily, which is why I think maybe problem 3 is over too easy. Unfortunately, well, not really everybody are able to write problem number 3 correctly. But I mean, well, this is really the same idea of either problem 1 and problem 2 for the problem 3, which is, suppose you have a function f, which can be written as the convolution of 2 functions, and g, h are both integrable. Okay, and I ask you to show that the Fourier coefficient or the Fourier series of f converge uniformly. So if you want to show the Fourier series converge uniformly, you have 0 way to prove, right? You have 0 way to show that. One is if you have this function is itself a C2 function, then that's good. We can use theorems that we proved in class as to say that, okay, all the Fourier coefficient is of order 1 over n squared. So the Fourier coefficient is it converge absolutely. So this function, the Fourier series of this function converge uniformly. That's totally fine. Or we can also use this kind of thing, right? If this function itself is continuous, plus the Fourier series of the Fourier coefficient of this function converge absolutely, then this function's Fourier series also converge uniformly. Okay? So we can do it like that. By the proposition of convolution that we learn, we know that the convolution of 2 integrable function gives you a continuous function. This is free, right? You can get it for free. So if you want to show the Fourier series converge uniformly, you just need to show the Fourier sequence or the Fourier coefficient converge absolutely, right? Then what is the Fourier coefficient? You want to show this one less than infinity. But what is this one? Well, F is G convolved with H. So you can write it as G times H, right? So which means we can run the exact same thing here. By Cauchy-Schwarz inequality, what we have is the little L2 norm of Gn and the little L2 norm of H hat n, right? Or you can write it, okay, it's less or equal than the summation of all the n, G hat of n squared with power a half times of all the n, G hat of n, well, H hat of n squared with a half. Okay. Then by either Passavant identity or another thing you want, you can get this is less or equal than, well, this inner product of F and G, well, G and H, right? So it's less or equal than, or you can even write this term to be the inner product of, it's actually equals to the inner product, the integral of G and H, and you take the, well, because it's actually with F's value, okay? So it's less or equal than gx squared dx from minus pi to pi, 1 over 2 pi with power a half, and integral from minus pi to pi, hx squared dx with power a half, 1 over 2 pi. Okay, and you know that f, well, g and h are both integrable. So which means g is bounded above, h is bounded above, so it's less or equal than some constant, which is less than infinity. Okay, so which means f, the Fourier coefficient of f converge absolutely. So we are done. Okay, so you should get this, well, this chain of result, saying that, okay, if you want to show the f's Fourier coefficient, f the Fourier series converge uniformly, then you may try to say that f is continuous and the Fourier coefficient of f converge uniformly. If you have this kind of idea, then you can show that, okay, that's easy, because it's just, you just need to control it by G and H, which is something very similar to this one. Okay, any question? Any question? Any question about the first 3 problems? So the first 3 problems are just testing you the basic property about convolution or Fourier series. Okay, there's a very basic properties about them. The first problem, for instance, is testing you, well, how to make connection with convolution and the Fourier coefficient. And second problem just ask you what is a very basic derivative property of the Fourier coefficient. And third one is just a combination. And maybe a little bit trick about, well, how to use the Cauchy-Schwarz inequality. Okay, so I just I try to see the first three problems as a whole thing. Any question? Okay, then let's see problem number 4. Actually, this should be problem number 5, because the problem we have the first honor code problem. Okay, so for problem number 5, we have the transport equation. AUT plus XUX equals to U. I think it's U, right? There's no coefficient in front of U. Oh, I'm sorry. 3x 2U, but it doesn't matter. Okay, just some constant. And the question is, first, you need to find a solution to this differential equation. Okay, and then I want you to show that the solution, all the non-zero solution of this PDE are just unbounded, which means it can tend to infinity. Okay, so let's try to solve it. Let's try to solve it first. Find the general solution, and then we can find, okay, whether the solution is unbounded or not. Okay, so how can we solve it? This problem is a problem with this 2U here on the right-hand side. So this problem has very similar method or very similar thing. The idea of this problem is very similar to the problem in your homework, right? If you remember, then I just changed one term here as in your homework, right? It's AUT plus BUX equals to some CU. And then you're asked to find the general solution to this partial differential equation, right? So you can either use that method or you can try to do it directly, as that's a hint I gave you in that homework problem, which is, well, you can somehow combine this term with this UT term so that it becomes one term instead of two terms. Then the problem becomes a little bit easier at least. Okay, which means let's try to combine this two terms, and it's AUT minus 2U, I put them together, plus 3xUX equals to 0. Okay, but before that, I think I should say, because this is a small trap on this problems, since I say A belongs to R, then you have to discuss whether A equals to 0 or not. If A equals to 0, then the problem becomes much simpler. If A equals to 0, that means you have the differential equation 3x times UX equals to 2U. Okay, so you have 3x UX equals to 2U. So that means UX, well, divided by U is equals to 2 over 3x. Then you can take the integral, and then what you can get is log U equals to, well, 2 over 3 log x plus C. Okay, so that means U is equals to some function times x to the power 2 over 3. You take the exponential both sides. But this part, you will need to solve this kind of ordinary differential equation. So if you don't really know how to solve this ODE, then that's totally fine. I didn't take too much point from you, from your solution if you don't know how to do it like this. But if you don't discuss, then I'll take off some point. Okay? I'm sorry, this is T. C is a constant. C is a constant in terms of x, so C must be a constant of t. But C must be a function of t. Okay? So you can see that this u tx or xt, which equals to some function times x to the power 2 over 3, if it's not identically 0, then we must have some t such that ct0 is not equals to 0, right? Otherwise, if ct for all the t equals to 0, then of course utx is equals to 0, right? Then that means we can have ut0 x is equals to ct0, which guarantees that the first term is not equals to 0, x to the power 2/3. And you can take x to be bigger and bigger and bigger, so this will tend to infinity as x tends to plus infinity. Okay, or minus infinity. It depends on the sign of ct0. It's just a number, so if it is a positive number, then x tends to, well, I mean, it doesn't matter. I will just, because x, it doesn't matter. I'm sorry, it doesn't matter because you have x to the power 2 over 3, so it will always be a positive number. And when x goes to infinity, then this number will go to plus or minus infinity. Depends on the sign of ct0. Okay, so if a equals to 0, we must have a function. If this function is not identically 0, then it must tend to plus or minus infinity. It's unbounded. Okay, this is when a equals to 0. If it turns out that a is not equals to 0, okay, then what we're trying to do is, as I mentioned before, as in the homework, you try to combine these two terms and make it one term, okay? Then you will have, you divide a both sides, what you get is ut minus 2 over au plus 3x over aux equals to 0. Okay? And how can we make these two terms together? Not so hard, right? We can just multiply e to the minus a, well, 2 over at. If we multiply this number, both sides of this, well, partial differential equation, what we will get is, okay, on this side, it will be u times e to the minus 2 over at t, okay, plus 3x over a times u times e to the minus 2 over at x. So, which means if we call this v function to be your u e to the minus 2 over at, then what we have is vt plus 3x over a vx equals to 0. So in order to find the solution u, you just need to find the expression, the general expression of v. How can we solve v? Well, the solution you can get from either the method of a characteristic line, as we discussed in lecture, or you can also check the stress book and they just tell you how to solve it. If you have x here, if you have a single x on your coefficient, okay, which is you can call this solution curve to be dx over dt is equals to 3x over a. So you get x is equals to e to the 3 over a t. Okay, so v on this characteristic line will not change the value. So vt tx should equals to some function, and you multiply by x e to the minus 3 over a t. Okay, this is the general solution for your transport equation of this form. It's on your textbook. So it only x equals to some constant, okay? X equals to this kind of thing. For different constant, you have different value of v, but on all this kind of curve, you will have the same value of v. It's just a different level set of v, okay? So that means v, well, utx must equals to f x e minus 3 over at times e to the minus 2 over at. This is the general solution for your transport equation, this one. Okay? Now, how to show it's unbounded? Again, same argument like this, right? It is not identically 0. That means there exists some m, f is a single variable function. There exists some constant, let's say something like m0, such that, well, f m0 is not equals to 0. Okay? So which means, well, if you have x times e to the minus 3 over at equals to m, then f this x e to the minus 3 over at is not equals to 0. It's a number, m0. Let's call this number to be a. Okay. So now what you want is you want t goes to infinity. And your x and t are on this line, which is x is equals to m0 times e to the minus 3 over at. When xt on this line, x is equals to m0 e to the 3 over at, when m and t, when x and t are on this line, your f, which is this part, will not equals to 0. But meanwhile, you can see that you can take t goes to infinity, right? So that means, well, if you have u, whatever t you gave me, and we can plug in x to be m0 e to the 3 over at is equals to a times e to the minus, well, I'm sorry, this is plus 2 over at. Okay? And t is actually arbitrary, so it tends to infinity as t goes to infinity. A is just a constant. Well, of course, if a is positive, then this goes to infinity as t goes to plus infinity. If a is negative, it goes to infinity as t goes to negative infinity. It will depend on the sign of a. It will depend on the so-called growth rate of this function. Okay? So that's how you can show it. Yes, it's a little bit twisted when you try to show it's unbounded. But if you have this geometric picture in your mind, then I think you are able to imagine why it goes to infinity. Any question about this problem? Any question? Any question?
So can we apply similar method to like all this kind of PDE with unconstant coefficient?
with unconstant coefficient, this part,
I mean, like the first part.
with this one,
Yeah.
there's a constant coefficient, right?
Yes, I mean like before ux.
Yeah, before ux is, well, it should be a constant coefficient, but if you have something that is not a constant coefficient, then the problem becomes much harder. Yeah, then the problem becomes much harder. And if you, maybe not much harder, but it's kind of harder. Because what you will want is, well, you want some function to multiply both sides of this equation such that this term can eat this term, right? So which means you would like to have something like e to something, you would like to multiply some functions that only depends on t, both sides of this equation. Otherwise, you cannot let this function to combine with this u, such that f of t times u, if you take derivative in t, then what you should get is ft times ut plus f prime of t times u. And as long as you can have this f prime equals to something here, then it's okay. Am I right? As long as you have, because you multiply f both sides of this equation, so as long as you have f prime of t equals to f times this function, then you are done, right? So which means if you have some little ft here in front, if you have little ft here in front, then if we try the same thing, for instance, a equals to 1, then ut minus ft, little ft u plus 3x ux equals to 0. And what you want is you want to multiply some capital Ft, both sides of this equation, so that it combines these first two terms, right? So you want ft ut minus ft, little ft u plus 3x ux times capital Ft is equals to 0. Okay, so now you want to make these first two terms like ft u, you take derivative in t. And it is f prime of t times u plus ft of ut. You want this to match with each other. This term match with it, but this term you want it looks like this. So you want f prime of t equals to minus ft little ft. Okay, so you still get a solution. The solution ft should equals to the antiderivative of little ft dt with minus sign. You take the exponential. You can divide ft both sides and take the integral, then you get logarithm of capital Ft is equals to the integral of this minus little ft. So capital Ft should equals to this. So you can still do it like that, but when this function is not only a function in t, if this function is a function in t and x, then this method will not work, because you don't really want, the reason you can do it like this is simply because this term, you can treat it as u times f x. Okay, so if you capital F will somehow depends on x, then this kind of method cannot work, because you will have extra term from this part. This will be a problem. If it doesn't depends on x, if it's just a little ft, then you can call this new v to be capital Ft times e. Then you will get Vt plus 3x Vx equals to 0. This will be okay. But if you have this in front of you, then, well, this method doesn't work. Okay? So it's kind of restricted. But not really restricted, it's a little bit restricted. Okay.
Okay, I see. Thank you.
Any other question? Any other question? So let's try to see what happens on problem number 6, okay? Well, actually problem number 6 is not really a PDE problem. It's just an analysis problem. It's I think most of you made some overthinking about this problem. It's not that hard, but you just need to be very careful on what I hint you, okay? So you have a wave equation, UTT equals to UXX. And the domain of this wave equation is t greater than 0 and x greater than 0, which is slightly different from what we've learned before, okay? And as a hint, you can use a D'Alembert formula without any proof. But you can see that if you try to use the D'Alembert formula, then the D'Alembert formula asks x to be arbitrary, not just a positive x. So which means maybe we should be a little bit careful about it, okay? And we have the boundary condition ut at x equals to 0 is equals to t for any t positive. We have ux when t equals to 0 is equals to, I think, is x cubed, is x cubed e to the minus 2x, okay? And ut at x0 is equals to 0 when x is greater than 0, okay, on the domain. Okay, so this is very similar to the Euler problem. So let's try to use the D'Alembert's formula and see whether we can find the solution or not, okay? From this differential equation, we can always try to do some change of variables and then write it as u c eta equals to 0, right? So we can say that the general solution of this wave equation must be able to write as f x minus t plus g x plus t, where f and g are two functions to be determined, will be determined by the initial condition, right? uxt is equals to this. Now the question is, how can you find this capital F and capital G? Right? Is that clear? It's just a D'Alembert's formula. You don't need any other method or idea about it, because it satisfies the wave equation. For any F and G, it satisfies this wave equation, okay? So we just need to use the condition to find F and G. How can we find them? Okay, let's try to find them. Let's see what condition we have, okay? Maybe let's try to see this condition first, because it seems most non-trivial, okay? ux0 is equals to this function, okay? So which means when t equals to 0, you should have fx plus gx equals to x cubed e to the minus 2x. And if you take derivative on t and evaluate at t equals to 0 is equals to 0, so you should have, well, minus f prime of x plus g of x, g prime of x is equals to 0. Okay? Oh, it seems that we are able to find this f and g directly, right? F and g are just a single variable functions. So from this two, it seems that we can find that, okay, the difference between f and g are just a constant. So we will have fx is equals to gx plus some constant So we should have 2 times fx minus c is equals to x cubed e to the minus 2x, right? So you should have fx is equals to c plus x cubed e to the minus 2x divided by 2. Okay, and then you find that, okay, even though we have this expression of fx, but if we plug into our u and take derivative in t and plug in x equals to 0, well, we don't really have this condition to be satisfied, right? We don't really have this condition to be satisfied. And you can see that it's a very bad thing, and well, this u x t should equals to what? It's very complicated. It's x minus t to the power 3 e to the minus 2 x minus t, right? And divide by 2, and you have plus c here. I think you should have this gx, you have minus c, gx is fx minus c, so you should have, you should minus c here, so you don't have any constant in the expression of u. This is your u, okay? And you can take derivative in t and evaluate at x equals to 0. But you find that it's not equals to t. Now the question is, why they don't agree with each other? It seems that the problem is overfitted. It seems that the problem is overfitted. You give me 3 conditions. It seems too much.
Oh, so there is a solution. Wait, so you would say that there is no solution because we have a contradiction?
Well, but if you try to see, if you try to look at it, you find that, well, it seems that we don't really have a lot of conditions, right? We don't have a lot of conditions because you have 2 derivative in t, 2 derivative in x. When you have 2 derivative in x, you should have 2 conditions, right? 1 condition, second condition. When you have 2 derivative in t, you should even have 2 conditions in t, right? So it seems that we don't really have a lot of conditions. This may not be good enough, right? So what we need to double check at this moment is whether we copy everything down or not. We want to say that, okay, this u satisfies this boundary condition. Okay, satisfy this boundary condition. But what is a domain? F and G satisfy this boundary condition when x is greater than 0. Okay, this is very important. So F and G satisfy this condition when x is greater than 0. So which means we can only solve capital F and capital G for positive number, for x to be positive. Well, I mean, is that enough? Because, you know, for this, you also have x and t to be positive. So if you have this solution, this capital F and capital G to be positive number, it seems no contradiction, right? It just needs a positive part of this function. You don't need anything else. But if you look at it, you find G, well, for G, you only need the condition, well, you only need the information of this function G when x is positive, right? When x is positive, t is positive, then g evaluates as something positive. That's okay. But for the real solution, if you look at this part, you find that you will need sometimes f evaluate as some positive number, sometimes maybe t could be greater than x. So you will need, in order to write the solution, the information of f at the variable which is negative. Okay, so the only information about the positive part of this function is not enough. Otherwise, you don't know what this term should express as. You see, when x is less than t, this is f as some number which is negative. But from these two equations, you can only solve f and g for positive input. Okay, this is a crucial observation, which is very important. Which is why when we try to solve these problems, we need another condition. Okay, so if you write it down, what kind of condition we need? If you find ut, okay, ut, and evaluate at x equals to 0, what you get is f prime at negative t with negative sign in front, plus g prime at t is equals to t when t is greater than 0. Okay, so in OR, what are you trying to solve is a problems about functions. You have 3 boundary conditions, so you have 3 equations on f and g, and let's write them very carefully. First equation is fx plus gx is equals to x cubed e to the minus 2x when x is greater than 0. This is condition 1. Another condition is minus fx prime plus g prime x equals to 0 when x is greater than 0. Okay, and the third condition is minus f prime of minus t plus g prime of t equals to t when t is greater than 0. So this problem, you can see it is a partial differential equation problem, but it's rather a functions problem. It's an algebra problem, or it's just a calculus problem. You just want to find the function f and g satisfy these 3 conditions. And you can see that from the first 2 conditions, let's say 1, 2, 3, 1, 2, as we mentioned before, what we get is fx is equals to gx plus a constant c, right? For x is positive, and well, fx is equals to 1/2 x cubed e to the minus 2x plus I think it's plus c when x is positive, or gx is equals to 1/2 of x cubed e to the minus 2x. I think it's minus c, right? When x is positive. This is something we just get from the first 2 equations. These 2 things gives us the information about gx when x is positive, fx when x is positive. Then for the negative part, as we mentioned, for the negative part of this function f, we can get information from the third equation, right? The third equation just tells you what happens, what is the relation of f x when x is negative and g x when x is positive. Okay, So from the third equation, what we get is let me make sure I did the calculation correct. Yes, I think I made the calculation correctly. Yes, I think I made the calculation correctly. So from the third condition, what we should get is, okay, f prime, if you take the antiderivative of this guy and this guy, what you should get is f prime of, well, minus t, let's call this minus t to be a new variable, that's a u, okay? F, well, where u is a negative number. Maybe let's not use u, let's use what variable we should use? Maybe let's call it s. When s is a negative variable, then what you should get is f prime at s is equals to this t is minus s and minus g prime of minus s. Right? This is what happened. So what it is? Well, it is minus s minus, if you plug in this s, this g with s is 1/2 minus s cube e to the minus 2 minus s minus c. Okay, so it's minus s minus 1/2. Well, you should have plus sign, right? You have minus, minus, you have plus sign.
Okay, sir.
You,
I think the sign was wrong.
which sign? This is minus, right?
No, in front of G, it should be plus.
In front of G, I think it's T minus G prime, right?
Yeah, in the other side.
You are right. You are right. Wait. Then, wait. I think I'm right. Let me see. So it's partial T, and you get this. Let me see whether I got something wrong here or not. Let me double check whether I'll get something wrong here. Okay, it seems you are right. I got some sign wrong here. So you have this one, so you have plus s here because t f prime minus s plus g prime minus s is equals to s minus s, right? So you have this f is equals to plus plus. Yeah, you're right. I'm sorry. This is plus, this is plus, this is plus, this is minus, and minus 2s plus c. Okay. I think I'm right at this moment, right? This is s minus 1/2 of this. Am I right? I hope I'm right. So that means, well, wait. Sorry, we should take derivative of this g. Then that's too complicated. I'm sorry. Let's rewrite it. So it's f prime of s is equals to s plus g prime of minus s. Okay. So if we try to take the antiderivative both sides, what we should get is let's take antiderivative both sides. instead of write down this g prime of minus s, because g prime is too complicated. It's we have to take the derivative of this guy. So fs should equals to, yes, fs should equals to some constant c0 plus s squared with a half plus g of minus s. Okay? With negative sign. Because if you take the antiderivative of this one, then you should have a minus sign in front by the chain rule. You can see that if you take derivative both sides, then you get this one. Okay? I hope I'm not doing wrong. This is minus g of minus s. Okay? That makes life much easier. Okay, so it's c0 plus 1/2 s squared, okay, minus g minus s. G minus s is, well, it's 1/2 and minus s cubed e to the 2s minus c. So it's c0 plus 1/2 s squared plus 1/2 s cubed e to the 2s plus c. Okay, so you get this, where s is a negative number. Now, okay, any question? I just did some algebra here, and this algebra is a little bit messy, but well, eventually I think I'm doing correct. Yes, we can definitely combine this 2 and 3 and get something. But we get this. So we get the expression of f when s is less than 0. But the last thing we need to double check is, well, we need to check f, capital F, is continuous at 0. Otherwise, well, we cannot get a closed solution. So f0 is equals to, from this side, is equals to 1/2 c, and from this side is equals to, well, c0 plus 1/2 c, right? So c0 is equals to 0. So what you get is f is equals to this one, 1/2 x cubed e to the minus 2x plus c when x is positive. And this one, 1/2 x squared plus 1/2 x squared x cubed e to the 2x plus c if x is negative. So the solution can be written as, again, two things. One is 1/2 x minus t cubed e to the minus 2x minus t plus 1/2 x plus t cubed e to the minus 2x plus t, which is f x minus t plus g x plus t. When x minus t is positive. Another part should have this expression. It's 1/2 x minus t squared plus 1/2 x minus t cubed e to the 2x minus t plus 1/2, this is still g, x plus t cubed e to the minus 2x plus t. This part is when x is less than t. Okay? Then this will give you the correct answer. This problem is not really a PDE problem. It's just a functions algebra problem. Right? We don't use anything about PDE. But we do find that for this problem, well, it can tell us the boundary condition for PDE, something is really messy. But you still get a consistent of the problem. Any question? Any question about this problem? Any question? Any question? So you just need to solve this 3, okay? And I just do some calculation here, which is some calculation from 101. Okay. So it's already 4:30 now. We still have one problem left. So let's take a 10 minutes break, or maybe let's finish this questions, and then we can take 10 minutes break so that you can ask me something. Okay. Let's finish the last problem. It is not so hard. So let's finish it. So for the last problem, is for this problem, to be honest, I think it is really something similar to the problems you have done in homework 2, right? You have done that problems in homework 2, which is to solve the Laplace equation on the rectangle domain. So I thought this problem is something you should be familiar with. Unfortunately, it's not that easy. I just change a little bit, but then it becomes, well, kind of harder, kind of very hard for you. Okay, so that is, you have ut is equals to 4 times uxx plus 7u when x is between 0 and pi t is positive. And you have the boundary condition u0t is equals to 0 and u pi t equals to 0, and for t is greater than 0, and u x0 is equals to cosine x to the power 4 minus 1. Okay, you have this initial boundary value problem. Okay, and we want to solve it. So if you want to solve it, almost the only way for us to solve such kind of a heat equation is by separation of variable. Okay, this is the only way we know. So that's trying to do the separation of variable and to see what kind of solution, what kind of function could be a solution and to this partial differential equation, and how can we use this kind of function, do some linear combination to match our boundary condition. Okay, so that's trying to say, do the separation of variable. This is always the correct way. So let's say utx is equals to something about, let's say, xx times tt. Okay, to make it well, more intuitive. Then if we plug in, what we find is, okay, you have xx t prime t is equals to 4, well, x double prime x t plus 28. Well, I didn't do a good number here, but it's okay. It's not a big deal. Okay, xx tt. And then what we want to do is, for separation of variable, what we want to do is we put everything that depends on x on one side and anything depends on t on the other side, right? So if we divide x and t, then what we will get is, okay, you have t prime over t, t prime over t is equals to 4 times x double prime over x plus 28. since you have x double prime here, so it seems a little bit too hard. So maybe let's move this plus 128 to the right-hand side to make life easier. But this doesn't matter, okay? Now we can use our old trick, then this equals to some lambda, okay? And still we don't know what we don't know. What is the sign of lambda, for instance? We don't know anything about lambda. Whether lambda is integer or not, we don't know that, okay? So then, well, let's see. If we want to solve it, for instance, if we want to solve it here, then what we will get is x double prime x is equals to, well, lambda over 4 times x. Then this does tell us something, right? It tells us if lambda over 4 is a positive number, then we can get x is exponentially growth or decay, right? Then we don't have u0t equals to u pi t both equals to 0. So which means we must have lambda over 4 is a negative number, right? So what we can get is then x, as I mentioned, x double prime is equals to lambda over 4 times x. So x must be able to write as cosine and sine, okay? So it's a times e, well, a maybe a e to the power square root of lambda over 4 times x plus b square root of lambda over 4 with negative sign times x, okay? So without loss of generality, let's say lambda over 4 is minus m squared. We didn't use m, okay? So it's minus m squared. Then x, just for simplicity, we don't know whether m is an integer or not at this moment. So x is equals to a e to the I mx plus b, because then it depends on m, bm e to the minus I mx. Okay, that clear? So, well, that's easy, right? Then what we want is xm to be satisfied this homogeneous boundary condition. For simplicity, we don't care about this one because it's over too complicated, but we do want it to satisfy this homogeneous boundary condition, which means when x equals to 0 and pi, it should equals to 0. Right? So that means we probably want this this m to be integer, and xm of x should be something, let's say, let's still use am, little am, sine mx. Okay? Because otherwise you don't really have this both 0 and pi equals to 0 evaluated. Okay? So this is your m. This is your solution of xm. Okay, for different m. Then, so we can plug in to this equation t prime over t minus 28 is equals to lambda. Lambda is minus 4m squared. Right? So we will get t prime over t is equals to 28 minus 4m squared. Whatever it is, it's just a number, right? This, you gave me a number, the value of m is just a number, right? So which means t is equals to e to this number, 28 minus 4m squared t. Okay? So that means we do get a series of or a family of solutions which satisfy this homogeneous boundary condition. Sorry. Let's say xt is equals to this kind of thing. Am times some other am times e to the 28 minus 4m squared t times sine mx. Okay, so we want this kind of function to do some linear combination to match our final boundary condition. U is equals to the summation of such that U at x0, because U automatically will satisfy this PDE, and it will satisfy this boundary conditions, and we want it satisfy this one, then we are done, right? It satisfies both this and this and this condition, then U is a solution, hopefully. So U x0, we want it equals to cosine x to the power 4 minus 1. Okay? So that means we want, well, this U, which equals to the summation of am, t equals to 0 is just 1, right? Sine mx to be equals to cosine x to the power 4 minus 1. Finally, we just need to find am such that this kind of Fourier expansion of sine series is equals to this kind. Seems very hard, right? Seems we have cosine, but we have sine here. How can we solve this problem? Again, since in this course, we just use this e to the in theta, so why don't we just go everything back to the e to the in theta so that the problem becomes much easier. So let's see, how can we write this cosine x to the power 4 minus 1 as e to the in theta form? Okay, we have to translate from cosine sine to e to the in theta, right? So cosine x to the power 4 minus 1 is equals to, again, we have 1/2 e to the ix plus 1/2 e to the minus ix is cosine x, right? So this is, well, 1/4 times e to the I2x plus 1/4 e to the minus I2x plus 1/2, right? And then you take square again. I hope I'm doing it right. So it's this one. Then we just need to take the square of this 3 terms. Okay, 3 terms, it's fine. It's not so hard, right? So it's this square, this square, this square, plus this 2 multiplied together, this 2 multiplied together, this 2 multiplied together, times 2. So it's, well, it's 1/16 e to the I4x plus 1/16 e to the minus I4x plus, okay, this is 1/4 and plus this 2 multiplied together, multiplied by 2. So it's 1/8. I think I'm right. And this 2 is 1/4 to the e I2x plus this 2, so it's 1/4 e to the minus I2x minus 1. Am I right? Am I right? This is 1/8. Yeah, I think I'm right. I think I'm right. Okay, whatever it is, it's just some linear combination of e to the I and x, right? So, well, we have, this is 3/8 minus 1, so it's minus 5/8. And this 2 will gives you, well, now you can see everything is just a sine functions, right? This 2, it will gives you something, what it is. This 2 will gives you, maybe this is not really sine function, but whatever it is, it's just a 1/16 e to the minus I4x, right? And plus 1/4 e to the minus I2x plus 1/4 e to the I2x plus 1/16 e to the I4x. Okay, so this is the Fourier expansion of your cosine x to the power 4 minus 1. Okay, I guess I'm right. 0, 0, then this is 1/8. And yeah, I think I'm right. So now the only problem is how can you match this sine function series to this guy, right? How can you match this two? Well, then we want this sigma am sine mx to be equals to this this kind of thing. Okay. So, well, then you have to compute it. Maybe let's try to write this sine x to be e to the imx minus e to the minus mx divided by 2I, and you have am here. So it is, well, it is, well, am over 2I. You take this, this kind of summation, e to the imx. For m is positive, and plus, I'm sorry, I should have a 0 here as well. When m equals to 0, I forgot one thing, I'm sorry. When m equals to 0, then you have x, well, when m equals to 0, you should have a 0 times t times e to the 28t here as well. Should I have this term? Should I have this term? Probably no, I'm sorry. Because then this term will disappear. When m equals to 0, I think you should have this u to be 0. No additional term here. Okay, then you should have m is less than 0 and am over 2I e to the minus imx. Okay, so, well, I think that's it. I think that's it. Yes, probably, yes. I think then you will get this and this and this and this. Adjust your Fourier coefficient and yes, I'm sorry, but probably we shouldn't write it like sine functions because then this makes the problem a little bit complicated. Maybe I should keep this kind of ways and say that, okay, when m equals to 0 and m equals to pi, they both equals to 0. So that means a minus b equals to 0, an minus bn equals to 0. That will be, maybe that will be a little bit better. Okay, I'm sorry, but maybe I have some mistake when I setting up this last problems. But anyway, I hope the idea you get the idea of the last problem. Okay, probably I got some mistake here, but the idea of the last problem is quite easy. It's just that you try to match this kind of series of functions with your initial condition. Okay, and when you try to do it like that, you just need to try to write it as a Fourier expansion. Add some Fourier expansion, and then you ask this this function to match it. Okay. I think I'll double check with my calculation here. Probably I did something wrong somewhere, but well, probably I will just let you know when I upload this this lecture notes. Okay. And other than this, it seems that I didn't finish it to the very end. But other than this, any question about this problem? Any question about this problem? I believe I made some mistake somewhere, because it shouldn't be, you shouldn't have this kind of constant coefficient here. No, whatever, yeah. Any questions about this problem?
No, not really.
Yeah, but well, keep in mind, maybe I setting up this kind of initial condition is not a good idea. But keep in mind, for instance, if I write here something like sine x to the power 4, okay, instead of this cosine x to the power 4 minus 1. Suppose I set it like sine x to the power 4, then I hope you are able to find this kind of an, okay? But I believe if I set up this cosine x to the power 4 minus 1, it's still correct. But I just made some mistake somewhere. But anyway,
yeah, I think this problem is right, because
I think it should be right. But it seems I didn't match up this coefficient. But anyway, yeah, nobody really do this kind of stuff. So, well, unfortunately, so nobody really find any mistake I made, if I made any. Okay. Any question? Any question about this one? I will try to correct it. Any question? So yeah, let's have a 10 minutes break, and we will resume at 5:05. Okay. And if you have any questions about these exams, please let me know. Okay. Just well, just to try to ask me during this 10 minutes or later. Okay, after the class. Let's have a 10 minutes break.
Yay.
Okay, I think we should start now. And well, I think I made some mistake when I tried to set up this the initial condition for the last problem. So if based on what I'm setting, you have to compute this coefficient of your solutions this way. Okay, you multiply sine mx and take the integral from 0 to pi instead of from 0 to 2 pi, which makes the problem kind of harder because we don't know how to compute this kind of thing. But whatever, yeah, you'll still be able to compute it, or maybe I should set it as well, the initial condition should be sine x to the power 4, then you are able to solve it. Okay, but anyway, yeah, this is nothing. So for the last problem, I think well, most of you don't really get the idea. That's a problem. Okay, and to match up the initial condition is something not so important, but to go to something until the last step is something very important. Okay, you should be able to try to get the idea about how to solve the problem, or what kind of procedure you should do when you try to solve the problem. Okay. So again, any question about your midterm? Any question about your midterm? Any question?
I only have personal questions and
Okay.
like no.
We can discuss in my office hour, which is after class. Okay. If no more question, then let's just get a start. Well, about what we are going to learn about the Fourier transform instead of the Fourier series. Okay, and of course today is Thursday, so if I talk too much about this part, then probably you'll forget everything on the weekend, and then I have to remind you again. But I think I still need to tell you some idea. I hope this kind of idea is it can get into your mind, and you can memorize it, and you can have it as your final motivation when you're trying to do some real problems in the future. Okay, so what we are going to discuss now is the Fourier transform, which is slightly different but somehow parallel to the Fourier coefficient or the Fourier series. Okay, so what is the Fourier transform? First, before we learn the Fourier transform, I should warn you that now, I think for the last few weeks, most of you suffer from those kind of sequence stuff, from those kind of uniform convergence and absolute convergence and convergent, this kind of idea, right? Good news is you don't need to worry too much about it anymore, because starting from Fourier transform, we will not really discuss those kind of sequence stuff, sequence result. But the bad thing here is, although we are not discuss this kind of sequence or series of functions, the convergence and the uniform convergence and so on, this kind of thing are still very important, because what we are going to talk about is not really the sum of some series, but the integral of functions. And now, starting from now, in this course, we will try to do some analysis based on integrals. Everything will be based on integrals instead of summation, infinite summation, but infinite integral, okay? So the reason why we are interested in the Fourier transform is very simple. Because, if you have some differential equation, if you have the heat equation, if you have the wave equation, if you have the Laplace equation, as you can see, some examples we introduced before, Well, for this kind of problems, the only thing you need to do is you try to do some expansion, right? And if you try to do some expansion, then naturally, what you will get is the coefficient of your Fourier series, if you have derivative of your function here, will become somehow super easy. The relation between the derivative and the function will be very, very easy. It's not just it's not like some derivative process, right? You have to take the limit, but as a multiplication process, which is why sometimes if you have some differential equations like this, and you suppose you already know something like u is periodic in x, for instance, in partial xx, u. Suppose you already know that u is periodic in x. Then what you can do is you can try to transfer this partial differential equation to an ordinary differential equation, okay? Because you know that u should be able to write as, suppose u is smooth enough, should be able to write as something like an depends on t e to the in x, right? Then the reason why I say this partial differential equation will change to an ordinary differential equation is, well, if you only consider this coefficient on the right-hand side, the corresponding coefficient or the corresponding Fourier series will becomes, take partial xx, you take partial xx term by term, then what you will get is n squared with minus sign, right? And an of t e to the inx. This is your right-hand side. And on the left-hand side, what you will get is, okay, you will get a prime t e to the inx. Okay, and by the uniqueness of the Fourier sequence or the Fourier series, you must get starting from a partial differential equation to an infinite many ordinary differential equation. Right? So, or if you try to write it in this kind of way, then what we should get is, okay, this you should get something like f or u hat of n, which is a function on t, should satisfy d over dt is equals to minus n squared u hat of nt, right? And then this partial differential equation becomes a family or a system of ordinary differential equation. Moreover, this kind of ordinary differential equation for most of the PDE are quite easy to solve. Okay? So which means if you are asked to solve a partial differential equation in a periodic boundary condition in X, for instance, you are asked to solve it by using MATLAB, okay? Then how you can solve it? Well, what you can do is you can try to find all the Fourier coefficients of this function. May depend on t, right? And this kind of comment or this kind of, this functions would be you take FFT of your function u. Okay? If you take FFT of your function u, then you get a series of you get a Fourier series of this function. Then what you get is, okay, after you take this FFT of u, what you will get is, okay, you get a series of functions, and this series of functions is a function of t, right? And now what you do is, okay, you have a lot of functions. You will try to solve an ODE. In MATLAB, there is a function about how to solve ODE. So ODE is much easier than solving PDE, right? You can use ODE 2.3 or ODE 4.5 to solve this kind of ODE.
By the way, just to make sure, what chapter is that of the book?
Now we will discuss the Fourier transform, which is chapter 5 of our book. Okay?
Okay, thank you.
Let's tell you some intuition. It's a different story. As you try to solve an ODE, looks like this derivative is equals to something like n squared and FFT of u. Something like this. Okay? So which means you transfer a PDE to ODE so that it will be much easier, at least for the computer, to solve them. Okay? This is for periodic functions. And it's periodic at least in one variable. This is also why sometimes we call this kind of method the spectral method, because this kind of functions are so-called the eigenvalue, the eigenfunctions of Laplacian. It can be seen as the eigenvalue of the Laplacian operator, because Laplace e to the minus I n x is equals to n minus n squared and e to the minus I n x, right? So if you try to see it as an operator, this operator acting on this function is equals to some constant times e to the minus I n x. So we call this kind of method spectral method. But of course, then sometimes it may be slightly harder than this kind of situation, which is you may have ut is equals to some fx times Laplace u, right? In this kind of situation, you can, of course, do the same thing as we did here, right? You try to look at what happens on the Fourier side or on the Fourier coefficient of these functions. Then what you will get is, okay, is the derivative of each Fourier coefficient of u is equals to, this time it's not so easy, right? It's f hat, and this is multiplication. And if you, after next week, maybe, you can see that multiplication on this so-called physical science, if you take the Fourier transform, it can be written as some kind of operation, which is also the convolution type of operations, but as a sequence convolved with this kind of sequence. Okay, but then you can see that it must, it is actually much more complicated, right? And you have to deal with some kind of convolution just because in your OD, in your PDE, you have a multiplication. So in order to deal with that, there is so-called the pseudo-spectral method. In numerical analysis, you have this pseudo-spectral method in order to solve this kind of issues, which is when you try to find this Fourier coefficient, it seems that if you try to find them in OR, then it's over too complicated. So how can you find those kind of Fourier coefficient? Then maybe that's not very hard, right? You just try to find the Fourier coefficient of this guy. Then if you try to find the Fourier coefficient of this guy, it's just some constant multiplied by the Fourier coefficient of it. Okay? And then what you're trying to do is you try to use this function to multiply it. And then, okay, you get a new function. Okay, you have this kind of function, but you don't know how to take this derivative on this function by MATLAB. So what you're trying to do is you try to find the Fourier coefficient of this new function so that you don't need to take derivative on MATLAB. Okay, so this function becomes fx on the right hand side. It becomes fx times the summation of minus n squared times u hat n t e to the I n x, right? So this step, if you use MATLAB, is super quick. And then you try to compute this function, the derivative, the Laplacian of u, very easily, because it's nothing but just you take the Fourier transform in order to find this coefficient, and then to use this kind of constant, multiply it, and then you try to take the so-called inverse Fourier transform to get the function back. Okay, and then you try to use this function to do the multiplication. Multiplication is much easier than this this convolution. After that, you get a new function, and then you get a new function, you take the Fourier transform of it, or try to find the Fourier coefficient of it. Well, this is some kind of idea about how you can really solve a particular problems by using this pseudo-spectral method, which is something I hope you could understand after we finish this Fourier transform part. But so after that, well, maybe I should say what really is Fourier transform. Well, let me formally write what is a Fourier transform, because after you know what is Fourier transform, you can see that for Fourier transform is something very flexible. You can try to do the Fourier transform of a function and transfer it to something else, and so on. Okay, I think from your midterms, I do find somebody who used a Laplace transform to solve some problems. That's really good if you know that, but if you don't really know that, well, you should be careful about the Laplace transform. So what is a function's transform? A transform of functions, basically, you can think it is something like an operator, which if you give me a function, I can give you another function. This could be seen as a transform of a function. For instance, if you give me a function fx, I can definitely transfer it to be a function fx minus a, where a is a constant, for instance, fx minus 1. Then from fx to fx minus 1 is a transfer of a function, right? This becomes a new function. Or fx, you give me this function, I do a multiplication by 2. Then this is your new function. This could also be a transform of a function. For the Fourier transform, what it is? For the Fourier transform, we always denote it as f hat. Okay, you give me a function fx, then I will transfer it to another function. Then for simplicity, we change the variable to represent another kind of function. Formally, this function, the Fourier transform of a function, sometimes we use this kind of notation, means the Fourier transform of a function f is an integral, which is an improper integral from minus infinity to infinity fx e to the minus 2 pi I x c dx. Seems very complicated, right? Seems you have a lot of things on this power. But if you try to compare this with the notation we had before in the Fourier series, you'll find that it is really similar, right? What is f hat of n for a periodic function? It is nothing but 1 over 2 pi from minus pi to pi fx e to the in minus inx dx. Okay? The only difference for this power is here we have a 2 pi. And here we don't have a 2 pi. But that's just some constant difference, right? So it doesn't change a lot. It's just we change this n with integers to some c, where c is in R. Okay, so it's more or less like we do a Fourier transform, some kind of this kind of Fourier transform to a periodic function, then we somehow get not really a function on R, but a function on integer n. Okay, so this is how you try to connect these two guys. Then, if you try to do the Fourier transform of a function, I will not show anything rigorously today, but I'll just give you an overview about this kind of thing. If you try to do the Fourier transform of a function, then you get a new function. The good thing here is, well, if you try to do the Fourier transform of a function, it will have all the good properties as this guy, okay? Which is, if you take derivative of this function and take the Fourier transform, it is very nice. It just equals to 2 pi I c times f hat of c, which is some constant times c times f hat of c. Okay, so similarly, well, you have something similar here, right? F prime at n is equals to I n f hat of n. So it is almost the same here. You just change this discrete n to this c. Okay. And another good thing here is, well, if you try to do the convolution of two functions, of course, what is a convolution of two functions? It is slightly different from the convolution of two functions in a period who are periodic. It is just f x minus y g y dy, this kind of way. Okay. And the good thing here is, if you take the convolution's Fourier transform, it is the Fourier transform of f times the Fourier transform of g. Okay. And this really gives us a lot of good information about this transform. Moreover, you know that as long as you know all the Fourier coefficients, you can somehow transfer it back to the functions by saying that, okay, this function more or less should equals to this f hat of n e to the I n x, right? More or less should equals to this. So you can recover your function by this Fourier coefficient. Similarly, what you can do is, well, if you have the Fourier transform of your function, the good thing is you can get back to your function by some other transform, which sometimes we call it check, okay, which is a reverse of hat. And then you can get fx. You can get fx back. And what is a check operation? Basically, you can find that if you do the Fourier transform of the Fourier transform of a function, what you will get is this function with minus x here. So which means if you take the Fourier transform 4 times of your function, you will get your function back. Okay, so which means for Fourier transform, well, it will have this kind of very good properties, and you can even get it back from the Fourier transform of the function to the function. The reason why we are so interested about the Fourier transform, again, is very simple. It's simply because we want to solve, for instance, this kind of heat equation or Laplace equation. And then if you try to solve such kind of equations on the whole space, now we don't want U to be periodic in X, right? Then you can do the Fourier transform both sides on X. What you will have would be U hat of C, right? You take d of partial U hat is a function of C and T. You can take partial T here, because if you take the Fourier transform, you can imagine it doesn't matter whether you take the derivative inner part or outside, which will becomes you take a partial X both, well, twice, then that means you take this kind of thing, multiply it twice. It's minus 4 pi squared times cos C squared times U hat cos CT. Okay, then it becomes an ordinary differential equation instead of a partial differential equation. So you can solve U hat of cos CT to equals to, well, now it's something you just need to do some kind of ODE stuff. It's just e to the minus 4 pi squared C squared T, right? Because then times F cos C. And this would be the solution to this ordinary differential equation. Then what you want to do, or what you need to do, is you just need to take the check operation, right? Then you will get is equals to the original function. So you do get a closed form of the solution to the heat equation by simply take some Fourier transform both sides of your equation, right? You can change the derivative to this multiplication. So this is why we are so interested about this kind of transformation. It's just because it's so nice. It's so nice for us to do this kind of, well, analysis of PDE. We only need to study them by this kind of integral estimate. So I'll stop here, and starting from next week, we will rigorously define what is a Fourier transform and how we can use them to solve a partial differential equation. Okay, now it's my office hour, and if you do not have any questions, feel free to go.